Okay, well, I'm about coming to the end of the CH series if I can help it. I might even be coming to the end of my career here on YouTube. You know, the career that pays nothing. But I want to throw out one more idea, and this is in response to a person I'll call the professor, who raised a very valid objection to my claim that if CH is false, there exists an A such that all if not to the power of A is equal to all of 1, and that A would have to exist. And I guess if CH is false, then that A would be some abstract mathematical concept that would be neither finite nor infinite. It would be A. Okay. And first of all, he raised the objection that, well, what about what 2 to the what power would be equal to all if not? Okay, is there an A such that 2 to the power of A is equal to all if not? Well, I would say that there's a way we can sidestep that one. Okay, and the way we can sidestep that one is 2 to the power of, let's see, in this case we have all if not to the power of all if not is equal to C. That's equivalent to 2 to the power of all if not is equal to C. They're the same thing. So I don't, when it comes to 2 and all if not, we're talking about something that from the standpoint of higher level cardinalities would appear the same. It's a little bit like, might even be invoking some kind of relativistic position here. But 2 to the power of all if not and all if not to the power of all if not are the same thing. But it's a valid, it's a valid objection. And I have to give his objections consideration, which is why I'm going to question my own claim that the assumption that 0 times higher level cardinalities is not equal to 0 automatically affirms CH. I'm going to downgrade that to I believe that's the case, and not it's proven that that's the case. So, but I'm going to make a case for why I believe that's the case. You get my case? All right. So he questions this here, that all if not to the power of A is equal to all if 1. And I'm going to make a case as to why I believe that it does. Let's start off with these two assumptions here that are true regardless of whether CH is true or false. All if 1 is a subset of C. Now, if CH is true, then we can construct an all if, then the all if 1 here wouldn't be the all if 1 of Cantor. We could just construct a set that's a subset of C, call it all if 1, but really all if 1 would be C. Okay. So we'll say it's true whether CH is true or false, but in the plain meaning of how Cantor used all if 1, we would have to say that all if 1 is a subset of C that doesn't map to C if CH is false. But, definitely this last one, the second one, is true regardless of whether CH is false, and there's no equivocation on that one. I don't have to mince words. All if not is a subset of all if 1 either way. Okay. Well, let's focus in on a subset. What does a subset mean here? Okay, if I have the set of all fruit that I have in my possession, and I have a bag of apples, a bag of oranges, and a bag of grapes, and I'm going to treat these as organic units, call them subsets of all the fruit that I have. And I either have the bag of apples in the set or I don't. I either have the bag of grapes in the set or I don't. Or I have the bag of oranges in the set or I don't. So how many combinations of subsets of the set do I have? Well, it's 2 to the power of 3. That's 8. Okay, it's a combinatorics problem. So when we have here, we have, in a sense, I could have a subset of C with all if not members. Well, how many combinations of that will get me C? Well, you know that based on, let's say, an infinite string of zeros and ones. By the axiom of choice, you could have a set of an infinite strings of zeros and ones, and you have either zeros or ones, and that'll go, and that you can make a set out of that, and that's a subset of all the possible combinations of zeros and ones. Well, how many subsets are in the bigger set? Well, there would be all if not to the power of all if not. It would also be 2 to the power of all if not. Either would be correct. Okay. But the bottom line is this would be the total number of combinations of subsets of infinite subsets of this higher infinity here. Okay. Well, what about here? If all if not is a subset of all if 1, then we are talking about, then the question, that's a logical question to ask, what are the combinations of subsets of all of 1 that get us all of 1? In other words, if I'm going to call all of not a subset of all of 1, then it's logical to ask, based on my understanding of what a subset is. Now, if there's some higher logic to a subset where I'm wrong, then I have to revisit my argument. But I'm a simple guy. A subset of a set means that I can ask the question, how many combinations are there of those subsets that would get me the bigger set? So I'm asking the question, how many combinations of all of not get me all of 1? That would automatically invoke something like an A. Now, an A wouldn't have to be a real number. It would be some kind of mathematical abstraction, but it would have to exist. Now, is there a number that's neither finite nor infinite? Now, remember, I believe in the continuum hypothesis, and so I don't believe that, I believe actually that this A would be all of naught, okay, and that this all of 1 would be C, and that this would not be a less than sign, it would be a less than or equal to sign, okay, so, now, over here, that is, okay, over between the C and the all of 1. This would continue to be a less than sign. Okay, so that would be my philosophical prejudice. If the professor is right, and if there might possibly be a subset of R that doesn't map to R that wouldn't obey that kind of logical reasoning, then I would have to say that I would ask the question of whether that subset of R is on if I would have to ask the question, does this lesser than thing have any meaning? Could it not be lesser than or greater than, perhaps? Or some mathematical abstraction that would be off of the real number scale. So that'd be the question I would ask. Let's say we could discover a set that would obey these kinds of strange rules where it could be a subset of R, but not mappable onto R, but where you couldn't ask this question, it wouldn't obey the logical rules of combinatorics. Why couldn't it be lesser than or greater than, or something that would seem contradictory? So again, this is my case for CH. It's not a proof of, and I don't know if I'm going to spend too much more time on this because, well, life moves on. Anyways, mathematicians, listen, take up this challenge. Look into some of the ideas that I'm suggesting. You can take it a lot further than I can. You have nothing to lose but your tenure. All right, thanks a lot.